A major leap in AI progress is the rise of agentic reasoning, an approach that enables AI systems to plan, execute, and adapt like dynamic problem solvers, like humans, basically. It allows these models to break down complex problems, gather information, and respond in context, all while autonomously learning and refining their approach. Traditional LLMs could not do this kind of work. Give them a complex task like research edge AI deployment and write a solid report, and they'll often treat it like a single writing prompt. It will do as much work as with a super basic question. They will basically start answering right now and draft something that sounds structured but isn't grounded or verified. The problem isn't intelligence in the abstract. It's that there's no built-in habit of planning, checking, and adjusting mid-flight, mid-execution, mid-prompt. The first fix people discovered was chain-of-thought prompting. You tell the model to think step by step before answering. For larger models, that simple instruction can noticeably improve performance because the model first lays out a plan, search recent papers, skim abstracts, compare claims, and then synthesize. And for our research assistant, the prompt would sound like, before answering, think step by step about how you'll research and verify sources, then write the report. But this still wasn't enough, because in a single pass chain-of-thought setup, the model's thinking and its final answer come out as one uninterrupted stream. There's no pause to run tools, fetch fresh data, or verify claims before the model moves on and gives a final result. As a result, the model can write a plan and immediately draft a report without ever executing it. Engineering-wise, this also makes the output hard to control and parse. Because there's no separation or interrupt boundary, you cannot build an iterative loop where the LLM executes a step, observes the result, and uses that observation to guide the next step. Tool calls can't be executed, results can be inspected, and claims can't be verified before the answer is produced. To enable verification, tool use, and adaptation, we need to use separate planning and reasoning from the action answering phases. That separation is the foundation for two core patterns you'll see everywhere: ReAct and plan and execute. ReAct is a short for reason and act. It was designed to blend two things LLMs used to do separate: thinking through a problem and taking actions in the world. Humans do this naturally. You decide what to do, you do it, you see what happens, and that new information changes what you decide next. That's ReAct in a nutshell. The agent cycles through thought, action, observation over and over until it can finish a task. For example, when a research assistant is asked to research edge AI deployment, it starts with a thought like, I need recent, trustworthy sources, so I'll begin with a targeted search across credible academic and industry sites. That thought triggers an action. It runs the search. The observation is what comes back: titles, links, and a short list of candidate papers. Now the agent thinks again using that observation. It thinks something like, I should filter for more relevance and credibility, pick a few strong sources, check the venue, and confirm dates. That thought leads to the next action: fetch and extract the abstract and metadata. The observation is the extracted summaries and structured details that the agent can actually compare. With those in hand, it thinks, now I can synthesize. Let me compare claims, especially adapting numbers, and flag inconsistencies. Then it acts again, running a compare and summarize step. The observation here is the conflict. One paper reports a 40% adoption rate, another says 25%. And here's where ReAct really matters. That conflict doesn't get ignored or hand-waved. It becomes the trigger for the next loop. The agent thinks again that it needs a tiebreaker source, so it takes an action by searching for credible market analysis and observes a stronger third-party report. At that point, the final thought is basically, I can now resolve the discrepancy and produce the report. And the agent finishes by generating a structured write-up with citations, including a short explanation of how it handled the conflicting statistics. ReAct's big advantage is that it can steer as it learns. Each tool result becomes a new context so the system can pivot, verify, and recover from surprises instead of charging ahead on assumptions. The trade-off is that this loop can become expensive and slow when the task doesn't actually require much adaptation. That's where plan and execute fits a bit better. It's designed for tasks with a predictable structure where the sequence from input to output is mostly known in advance and doesn't depend heavily on intermediate results. A writing pipeline is a good example. Outline, draft sections, render diagrams, extract images, and then compile the final article. Plan and execute splits the process into two phases. First, the system generates a complete plan, and then it executes that plan step by step. This is often more efficient because it reduces how often you need to call the most powerful reasoning model. You use a planner, typically a capable LLM, once to produce a detailed order checklist, then an executor or a worker, which can be a lighter weight agent or even a simple loop that runs tools and carries out the steps. You only go back to the planner if something breaks badly enough that the plan needs to change. That separation tends to lower latency and costs compared to re-reasoning after every single tool call. In plan and execute, you can think of it as committing to a route upfront. Just like looking at Google Maps before going, then driving it fully, rather than stopping after every turn and replanning. One quick clarification before we go further is that plan and execute can sound similar to orchestrator worker, but the key difference here is where the orchestration lives. In orchestrator worker, the developer wires together workers with external rules. One worker searches, another summarizes, and another writes. In plan and execute, the model generates the plan and the system executes it. Both have a planner and both have executors, but in orchestrator worker, the coordination logic is written outside the model, while in plan and execute is generated by the agent as part of the reasoning pattern. Now let's take the same research task and see how plan and execute would handle it. You need to first prompt the agent to create a complete plan to fulfill the request. It will output a structured list of tasks like this. Then comes execution. The system works through step 1, then step 2, and so on, storing outputs as it goes so each step feeds the next. The system re-enters planning only if something major goes wrong, such as no relevant sources being found, or a step failing completely, or a downstream step can't proceed because the expected input wasn't produced. That's also the main risk of plan and execute. You are committing to a plan before you've seen the messy parts in reality. It's efficient when the world behaves as expected, but it can break when assumptions don't hold. That's why this pattern works best when you have a stable pipeline and clear interfaces between steps. And it's also why we usually want to build in safeguards for error handling and replanning. Choosing between ReAct and plan and execute comes down to 3 constraints: uncertainty, task structure, and latency and cost budget. If you expect surprises, conflicting sources, missing data, or weird tool outputs, you want an approach that can adapt midstream, like ReAct. If uncertainty is low and the steps are unlikely to change, you can use a more committed approach like plan and execute, where you decide the route upfront and then follow it. Now, let's bring the task complexity into it. If the task is small and simple, ReAct often wins on speed, because stopping to build a full plan beforehand, as in plan and execute, is just a lot of extra overhead. If the task is complex but predictable, same steps every time, plan and execute is usually faster and cheaper because one good plan upfront replaces a lot of repeated reasoning along the way. But if the task is complex and unpredictable, ReAct tends to win again because the ability to adapt is the whole point here. With plan and execute, you are more likely to hit surprises that force replanning, and that's where the cost and time pile up. Cost and quality can trade off too. We ran a little comparison on a structured data task of analyzing a CSV and generating a report, and ReAct was slightly cheaper, around 6 to 9 cents, but less accurate, around 85%, while plan and execute cost more, 9 to 14 cents, and achieved slightly higher accuracy, around 92%. But that's just one example. In practice, you rarely pick one pattern and stick to it in any case. The most useful systems borrow the strength of both. You use structure to stay on track and use loops to handle uncertainty when it shows up or when you expect them to show up. That combination is easiest to see in what people often call deep research workflows. Deep research systems are built for long horizon tasks like market analysis, literature review, or financial diligence, all jobs where one model call is never enough because the work spans many sources, many steps, many tools, and a lot of verifications. Instead of treating the prompt as write a report, the system needs to first turn it into a set of sub-goals. So if the task is to analyze the competitive landscape for quantum computing, it breaks that down into things like identify the key companies, collect recent research, scan patents, track recent announcements, and summarize sentiment and momentum. Once that high-level structure is set, the system executes step by step. But inside each step, it behaves more like ReAct. It searches, pulls data, compares sources, and checks claims. If it hits something messy or unclear, like conflicting statistics that we had previously, it doesn't just pick one and move on. It loops locally, finds a tiebreaker source, and only then continues. So the mental model is simple. Plan and execute gives you the global scaffolding, what the sub-goals are, in what order to tackle them, and what being done for a task really looks like. And ReAct-style loops handle the local uncertainty, missing data, conflicts, and verification inside each sub-agent or sub-goal. Some deep research systems scale this further by running multiple research workers in parallel under a lead coordinator. So the different sub-goals are handled at the same time, and the coordinator stitches the results into a single final cited report. Deep research systems are basically ReAct and Plan and Execute stitched together at the system level. What's changed recently is that the same ideas are showing up inside the models through what we now call reasoning models. Reasoning models are models that can spend budget on planning and, in many cases, interleave that planning with tool use. Instead of relying entirely on external orchestration frameworks, some of the reasoning structure is built into the model's behavior and the API's exposure. In practice, you'll see two common reasoning styles show up. The first is think, then answer. The model takes the prompt, does an internal planning phase, and then produces the final answer. Some APIs let you control how much thinking it does, like setting a higher or lower reasoning effort. For example, OpenAI exposes a reasoning effort setting from low, medium to high to trade off speed and cost versus depth. Claude exposes something similar through excellent thinking, which enables thinking and sets a token budget for it, which is really interesting. The second is interleaved reasoning, where the model alternates between thinking and acting. It can decide to call a tool, read the tool result, then think again and repeat until it's done. That's the ReAct loop embedded into the interaction. Thought, action, observation, thought, and repeat. This is also where tool calling becomes much more natural. Tool calling is still a back and forth between your app and the model. You send tools, the model asks to call one, you execute it, then you send the results back. But the model can handle the decision of when and why to use each of your available tools much better when it's in a reasoning model. So models are evolving, and that's really cool. But what's driving this shift in reasoning capability? A big piece is training. Many reasoning-focused models are post-trained using reinforcement learning to improve their ability to produce, correct, and verify solutions, and to choose tool use strategies that actually work. Okay, that's cool. But what does it mean for you as an agent developer? It doesn't mean you stop caring about patterns like Plan and Execute or ReAct. You still need them as mental models for how the system should behave because you are still responsible for the environment around the model. Tool design, tool permission, stop conditions, evaluation, monitoring, guardrails, etc. What's changing is where the boundary sits. More of the which tool should I use next logic can live inside the model, while your job shifts toward making sure the tools are well scoped, the objectives are clear, and the system is safe when the model makes a bad call. I have a very simple example. If you ask, check the weather in Paris tomorrow, if it's sunny, book me a flight. Even with a strong reasoning model, you still need to provide two things, a weather tool and a booking tool. The model can decide the sequence, check the weather first, then book, but your system has to enforce constraints. Like, don't book without confirmation, don't spend above X amounts of dollars, and log everything. Tool intelligence doesn't remove system responsibility. It just changes how much manual orchestration you have to write yourself, or cloud code has to write for you. When you build around LLMs, you're not really adding intelligence to a product. You are deciding how much uncertainty you are willing to tolerate. A workflow tries to eliminate uncertainty by forcing the world into a predictable shape. ReAct accepts uncertainty and manages it step by step. Plan and execute bets that the shape is stable enough to commit early. Reasoning models just change where some of that thinking happens, not whether you need it. So the real skill isn't choosing the fanciest architecture. It's choosing the smallest amount of structure that keeps the system honest about what it knows, what it checked, and when it needs to keep going. As always, we want to use the simplest system that works for our task.